Hey, so welcome to your lesson on electricity and circuits. Now that you know about static electricity, this is the next step, is to learn about electricity that is kind of the normal electricity that we think about that runs through a circuit. So let's go ahead and get into it. First of all, an electric circuit provides a pathway for electrons to travel. So when we take a look at a circuit, we look at the wires, we look at the components. That's what's happening, is that electrons are traveling through that circuit. The other idea behind the word circuit is the fact that you kind of start and end at the same place. Normally circuit means that it's circular, right? So when we deal with a circuit, an electric circuit, we have electrons starting out at one location, the power source, and then eventually returning to the power source as well. And as they go through that circuit, they lose some of their energy as it gets converted to other forms by different components that we call loads. But we'll talk about that later on. So here are some of the things that you are going to find in an electric circuit, and we're always going to find these four basic elements. First of all, the source. So the source of electric energy is your power supply. Maybe it's a battery, maybe it's a transformer that plugs into a wall, but that is your source. So it is what is giving energy to the electrons. The conductor, there's often many conductors, right? But the conductor is the wire through which current flows around the circuit. And then we have loads. Loads are items along the circuit that convert electricity into another form of energy. Things like light bulbs, motors, speakers, resistors, these are all loads. And what they do is, again, they convert electricity into some other form of energy depending on their purpose. And then finally, we have controls. A control controls the current. So a control is a switch or device that turns the circuit or device on or off by changing the flow of electrons. So when we have a switch, we can turn off the electron flow going through a wire by opening that switch. And we're going to get more into this as time goes on. But we're going to talk a little bit about schematics. An electric circuit can be represented by a schematic, which represents components of the circuit with symbols. And these are the symbols of different things. So wire, we just draw as lines, right? And we show connections between wires with lines intersecting. When we have just a single cell, that would just be two lines, one longer and one shorter. And so that would be something like a AA battery is actually just a single cell. When we have several cells together, that technically is called a battery. So then, we got a bunch of these together, a bunch of cells together in a line. And so we call that a battery, just another power source. Does this matter a bunch, the difference between a cell and a battery? No, we talk more about this later on. Lamp or light bulb, we have this kind of curvy thing in the middle and then a circle around it. This is meant to represent the filament of an incandescent light bulb right there. Switch is represented by a dot and then a conductor in between. So this would be an open switch. It's not closed, which means that current cannot go through it. It is in that open position. And then once the switch closes, this goes down, then current can go through because now it's just essentially a conducting wire. And then finally, we have resistor, which is this back and forth zigzaggy pattern. Resistors are meant to resist current, to resist electricity, and they do that by converting electrical energy into some heat energy. But it's a major component that we deal with. And sometimes we use a resistor to represent just a generic load. Okay, when we don't know what it is. So more explanation, a cell, a single voltaic cell, which makes up batteries. A battery is made up of a number of cells. So typically we have more than one. For example, if you open up a 9-volt battery, which you shouldn't do, don't open up your batteries. But if you did, you'd find that you actually have 6 tiny batteries inside of there that almost look like AAAs. They're slightly different size, but they're almost like AAA batteries. And then we have a switch, again, which is used to open or close a circuit. This is a type of switch called a knife switch because the middle is kind of like a knife. And again, here, when it's open, right, that is no current. When it closes and this swings down, then it's making connection. It's now acting as like a conducting wire, and that would be a closed switch or a closed circuit. Resistors. The resistor symbol, that back and forth, can represent any load. And load, again, is just electric energy being converted into other useful energies. Most loads resist the movement of electrons and convert their energy into another form of energy. And there's also an electronic component called a resistor that resists the flow of electric current. So here we actually have different pictures of different resistors, and the size has to do with the amount of current that would be flowing through it. The color of the background color, I think it has to do with the quality of the resistor, of like how certain the resistance reading on it will be. And then we have different bands on it, which actually tells you the resistance of that resistor. There's a code that has to do with the colors that will tell you how much resistance each one of these resistors provides. You don't have to know about the codes, you don't have to know about the colors, you just have to know that resistors resist current, that they essentially convert energy from the electricity into another form, typically heat, right? The resistor component, it is for sure heat. These are for sure heat. But when we use resistor just to mean any load, then we don't know. So when you draw a schematic, and we are going to do a little bit of drawing of schematics, but primarily we're just going to be doing building of virtual circuits and testing it out and stuff. But if you were to draw one, you should draw it with a pencil and ruler. The ruler is, of course, very important. So we get nice, straight, even lines on graph or unlined paper. You place components in a rectangular or square arrangement. So you essentially just kind of like place things in a way that makes sense. So it kind of fits a rectangular type pattern. Make conductors straight lines with right angled square corners. So again, we're all just dealing with squares and rectangles here. If possible, arrange your diagram so conductors do not cross, which takes some careful planning. If we do have to make a conductor cross, we just actually do a little jump. So we show that by, if we had one line like this, then our other line would just go like, and then jump over like that. And then draw neatly, making symbols a consistent size. Okay, so essentially just make a neat diagram. Keep it neat and tidy. So let's do an example together. I'm going to do this with the pen, okay, which is a little bit of the lazy way, instead of using the line tool, which would be better. But I want to go through the process without it being a horribly long time, so I need to instead use the pen. So even though I said draw with a ruler, hard for me to do in this kind of environment, right, with the pen thing. So just pretend like all the lines are straight, please. So draw a simple circuit of a light bulb powered with a battery and controlled by an open switch. So we're going to start by drawing our battery. So I have long line, shorter line, long line, shorter line. Let's go ahead and do 3 cells in that battery. So each one of the long, short lines is a cell. So I have 1, 2, 3. I just picked that randomly, no rhyme or reason for 3 cells. Okay, so now we're going to draw like this. My conductor here, let's put the switch right here. Okay, so here's my open switch. This can go out to, again, come to conductor. And then right here, I'm going to do my light bulb. So I'm going to go up, do my squiggly. Just like that. And then I'm going to draw a circle around that. There's my light bulb. Okay, so there is my circuit. I drew a simple circuit. And here's my open switch. As soon as I close this switch, it will connect and this light bulb will turn on. Okay, current is the amount of electrons. So these are ways that we talk about electricity. There's 2 main terms that we talk about when we talk about an electric current. We talk about the current and the voltage. Both of these are incredibly important. So current is the amount of electrons that passes one point in a circuit in 1 second. So measuring current is essentially measuring the number of electrons that are traveling through. The symbol for current is I. I know that makes 0 sense that it's an I, but it's an I. And it is measured in amperes, A, or amps, or milliamperes, milliamps, MA. Milli is just small m is the prefix that we use in front of the unit when we have milli. So what milli means is it's 1,000th of an amp. So when you think about a millimeter, that's 1,000th of a meter, and a milliamp is 1,000th of an amp. So that's what it says here, which is equal to 0.001 amps, in other words, 1,000th. So you'll see milliamp type measurements on different electronic components and stuff. Typically though, when we talk about like a current that's coming from a house, from an outlet or something, we're talking about amps. We're talking within like battery powered electronics and stuff, we're probably talking more about milliamps. But anyways, an amp is equal to 1,000 milliamperes, or 1 coulomb per second. So this is the unit that is equal to an amp. 1 amp is equal to 1 coulomb per second. So you learned about coulombs as a measurement for charge, and that is a ton of electrons. So when we have 1 coulomb's worth of electrons traveling through a circuit within a second, then that means that we have a 1 amp circuit. So in other words, 1 coulomb of charge passes a point in the circuit in 1 second. That's 1 amp. And I wrote full amp here. We just normally do an A. 1A is equal to 1 coulomb per second. But anyways, we're going to talk more about this later. So I know this is maybe slightly rushed right now, but we are going to get further into this another time. How do we measure current? We measure it with an ammeter. Okay, so this is a picture of an ammeter. Ammeters are often built into multimeters and stuff as well. But for an ammeter, we can use this to measure the amount of current going through a circuit. Schematic symbol for an ammeter is really easy. It's just an A with a circle around it. So that's how we measure the current. In order for us to correctly measure current, though, we need to make sure that the ammeter is, how do I put this? That all of the electrons have to move through the ammeter. So in order for me to put an ammeter in this circuit right here, I would full on have to break the circuit and put the ammeter right here. And then I could measure how much current is going through the circuit. If I instead did this, where it's still connected, but then I had the ammeter here, this wouldn't work. And the reason why it wouldn't work is that the electrons would just travel not through the ammeter, but they would travel through this wire, because the ammeter is going to give more resistance. So the current that is registered here would be much lower than what actually goes through the circuit. So when we put an ammeter in, we full on have to break the circuit. So we have to like break the circuit in order for the current to travel through there. All right, galvanometers are used to measure very, very weak currents. They're just big G. We don't normally use these very often, or this symbol, but just so you know that when we're dealing with incredibly weak currents, we have to use a galvanometer instead. Okay, so kind of a different device. Let's talk about voltage. Electrons have potential energy if positive and negative charges are separated. When positive and negative charges are separated, we have a voltage, which is a measure of how much electrons want to get from one side of the power supply to the other side. So for example, in a battery, chemical reactions cause electrons to be released at one terminal and drawn in at the other terminal. So it's all powered by chemical reactions. And electrons have potential energy because they want to move from one side of the power supply to the other. The desire of them to move from one end to the other, that's voltage. It's the potential difference is another term that we use. The potential difference between this side and this side. So potential difference is the difference in energy per unit charge between one point of the circuit and another. It's also called voltage. I have here water slide analogy. The idea is this: if we were to take a look at a slide where we have the top and the bottom, the height from the top to the bottom is kind of like the voltage. Okay, it's how much the electrons want to get from here to down here. So it's like a potential energy. So the higher up the water slide beginning, the more voltage we have compared to the end. Voltages are measured using a voltmeter. It measures the difference in the energy of electrons between 2 points in a circuit. So if I connect it to 2 points in the circuit, it will measure how much the energy drops between those 2 points. So an example of different voltages, a AA battery is 1.5 volts, a wall outlet is 120 volts that you plug devices into. Inside a microwave, I know it's plugged into the wall, but then they actually have a part in the microwave that converts, a transformer that converts the voltage from 120 volts to 2100 volts. So inside your microwave, you actually have a 2100 volt kind of like line in there. Just absolutely insane. The best way to kind of think about electricity or water, electricity, is to think about it as water flow. And that will help make sense of this whole current and voltage thing. So if I were to think about different like hoses and water guns and stuff, okay, think about it that way. Current is the amount of water that's going out of the water gun. So you got like one of those dollar store like water guns. It barely lets out water, so it's very low current. And then voltage is like the amount of pressure that that water has. So if you had a really high powered water gun, right? A lot of pressure, it's hitting really hard. So a super soaker would have like quite a high voltage, but not a super high current. But then if you had something like a riot hose, that's both high current and high voltage. If you talk about your piddly dollar store gun, the one, that's low current and low voltage, right? So that's kind of the idea. The higher the current and the higher the voltage, the more work it can do, okay? The more power we have. So high voltage with low current can't do much work. Think about like a water pistol. However, if there is a high voltage and a high current, it can do a lot of work like a riot hose. And wires are like the water pipelines that things are moving through, where the streaming water, I don't know, however we want to think about it, but that's what the wires are like. All right, so let's kind of talk about what's happening in a basic circuit. This is essentially the circuit that we drew with a cell powering a light bulb with an open switch. So at A, this is where the electrons are at their highest point. They are leaving the power supply at this location. So the electrons have a high energy here because they want to make it to the other side of this cell. So they have the highest voltage or potential energy, I should say, here. As they move through the circuit, right, they're moving through the conductor here to here. They don't lose much energy through the wire, teeny tiny amount due to friction, but very, very little. But as it enters the light bulb, electrons power the light bulb and they lose their energy to make light. So electrical energy gets converted to light energy from the light bulb, making this shine. So during this time, the electrons are losing their potential energy. Okay, so they're losing energy as it goes through. Electrons exit the light bulb with a lower potential energy as voltage has dropped, so they're now leaving with low energy. The switch, if it's closed, right, that would allow the electrons to move through. If the switch is not closed, none of the electrons can move. Electrons keep on going through and they go to the positive side of the power supply. And then from there, they're done. So once they reach the positive power supply side, they no longer have as much energy. Okay, so that is really a simple circuit. We've talked about current, voltage, how we measure it, all that kind of stuff. This is a good intro to electric circuits. And now we can move forward and kind of learn more about circuits, series and parallel and voltage and current, how to measure it. There's a lot of stuff here, but that's a good intro. All right, have a good rest of your day.